Okay, so yeah, I'm Torsten Hoefler from ETH Zurich. Sorry for the 20-second setup time. I wasn't as swift as I wanted to be. I'm heading the Scalable Parallel Computing Lab, which is about 15 people now. We're working on high-performance computing. And today I want to talk about distributed GPU computing with hardware overlap. So it's a slight change in the title, but you will see where this comes from. Of course, this work has been mostly done by my students and not myself, but I get the big honor to present because my students have to get actual work done at home. So as we all know, GPU computing, and I don't really need to advertise this much more, is the basis today of many of the computational challenges we are solving. When we've seen the weather and climate simulations, as Maxime talked about this morning, how to optimize very large multi-GPU systems and make this reasonably fast. This talk is kind of an extension to this, as we will see, because it moves from the node boundary from inside the node to across node from within CUDA. As we also know, machine learning is picking up, or is at a pace that is actually kind of close to crazy. And that will also go to multi-GPU systems, so to distributed computing, or is already mainly a distributed computing. And the last one, molecular dynamics, is more of the traditional HPC type workload, which more and more of these workloads are also moving towards GPU computing. But now let me actually get to the real point. How does the architecture of these GPU systems look today? So mainly, if we look at distributed memory computing, we always talk about multiple nodes, right? So we have two nodes here, node 1 and node 2. And each of these nodes has, of course, a GPU, otherwise we wouldn't be talking about GPU computing. The GPU comes with device memory in both of these nodes, and then it has a PCI Express connection, as Maxime explained us, most commonly, like not always, but most commonly, NVLink is coming. And then it's somehow connected to some, usually or very often, x86 CPU, maybe ARM soon, that has its own host memory and so on, and then we have a PCI Express connection to the interconnect, right? So this is how this looks like in practice. How do we actually program these machines? And many of you are probably familiar with this. So we have some code, and that is typically NVIDIA code and NVIDIA CUDA code when you talk about NVIDIA GPUs, which is, so you can also plug in OpenCL if you like. But the principle is basically the same. So you have a function that you want to offload to the device. You add some functional decoration to it. You basically say, hey, this function is to be executed on the device. And then every time you invoke that function, data transfer will be happening to the device, which you may or may not need to manage depending on the environment you're using. And then the device starts up and solves the computation. Okay, so this looks then really like this. So you launch a kernel with these parameters. And then, of course, what you need to do is you need to move the data back and forth from this host memory to this device memory. Right? This is just CUDA 101, and I'm assuming you somehow know this. But what's now getting a little bit annoying is if you actually want to communicate from this GPU to this GPU, what do you do? Well, today, what you would actually do is you would use CUDA memcopy. We know that we have GPU direct and all of these features, but in the trivial implementation, we would use CUDA memcopy to move it into the host memory and then to the other side. But somehow, even that data management does not matter. Even if we get this automated, as we've seen in some of DK's talks, we still have to issue MPI calls. And these MPI calls are almost always issued from the CPU, right, as we do this today. So basically, this CPU gets active and issues an MPI call. So why this is a problem? Well, if we look at the normal flow where we have this, so we have the device. So first we have the host. It sets up a kernel computation. We have the device that executes the kernel computation. Then we issue these mem copies. Then we sync the device. And this really means that, as we all know, the GPU has this wonderful mode of execution where it has multiple warps that it automatically switches whenever one warp is blocking for memory access. Right? So it has this pipeline of accesses going on in parallel, has as many operations as you can imagine floating in parallel. Actually, it has multiple tens of thousands of memory, open, outstanding memory operations going on at any given moment if the GPU is used at a full capacity. And the problem with this is now, well, this device synchronization will have to stop this pipeline, will have to drain the pipeline, and actually make all of these memory accesses consistent, meaning this whole thing comes to a halt, then copy this to the host, at least logically, right? Maybe not physically, but at least stop this, that we can issue these MPI send and receive calls. And then, well, we have to issue the cluster synchronization, which is now synchronizing with the remote nodes, right, which is implicit in MPI. We don't necessarily need to do this, but this is implied by the MPI send and receive calls. They have some synchronization semantics. So the very simplest synchronization in semantic is that a message cannot be received before it has been sent. It's kind of clear. So MPI receive will not return before the matching MPI send has been executed. And this is what I mean by cluster synchronization. And then once this is done, we again have to launch the kernel at the other side, at the host. Okay, great. The problem with this is, of course, that we have to, in order to program an MPI code, we have to mix two programming, a distributed CUDA code, we have to mix two programming models. We have to first understand CUDA, and we have to understand MPI. We have to understand CUDA to use the device, and we have to understand MPI to actually communicate among the nodes where the devices are plugged in. If you now think about this, well, why don't we actually communicate with the devices directly? Well, that's because of the history that we have, because we have been using MPI. What this also implies is that we have to duplicate some of the functionality between the device and the MPI, especially the functionality that we duplicate is the data layout. Because, of course, as we compute on the device, we will have a particular data layout. We have a particular loop structure, which is, of course, optimized to avoid all kinds of bang conflicts and have the perfect streaming of data and everything. But now we have to have this similar data layout at the device side, especially if we want to use the MPI facilities to move data back and forth, for example, data types. So we have some synchronization. And the problem is, of course, well, performance, as we are all doing high-performance computing. What does the device do while we issue the MPI calls? Well, you could, of course, pipeline this whole thing, that you have multiple logical threads going on in parallel, which means that the device executes just another rank's kernel at the time when you do this MPI send and MPI receive. But of course, if you have a bulk synchronous application, that is going to be relatively hard to make happen in practice. So, and in fact, this whole programming model somehow encourages the sequential execution, right? If you do at least look at the simple version, and this results in a rather low utilization of this very expensive hardware that we have. And if you look at the average GPU program, for example, the large-scale code Cosmo, which we're using in Switzerland to predict the weather, this is exactly what it's doing. I mean, it is waiting for the MPI to finish before it launches the next kernel. It's, of course, a waste because the MPI overhead is between 5 and 15%, depending on how you execute it, depending on your scaling. So now you waste immediately 5 to 15% of your GPU time to, I don't know, sleeping, waiting for the MPI thing. Okay, so, but now let me go a little bit more into detail and explain you, if you, in case you don't already know, how a GPU why a GPU is that fast. What does throughput computing actually mean? Because we will need this very soon, because we will extend this in order to combine throughput computing with a communication on a throughput computing device. So if you just look at this very simple GPU assembly code, so this is maybe SAS in this case, but I think it's more of a generic language. So there's the code we want to issue is a load of some registers, I mean of some data, of course. We have a multiplication and we have a store, okay? And then you probably know that the GPU cores will now execute this in a massive parallel way. So each of the threads of the GPU threads, maybe thousands, will execute these 3 instructions. And in fact, you will launch 1,000 threads on these GPU, or on your favorite GPU, but there will only be a very small subset of these threads active at any time. And it's using the parallel slack. It's actually a term introduced by Mark Sneer a very long time ago. The parallel slack to hide the latencies. Because what it's actually doing is as soon as the first one hits this load, it will just deschedule it. Logically seen, of course, in hardware something else happens. It will logically seen deschedule it and just schedule something else that can issue another load. So let's look at the execution of this guy with a large number of threads on a real GPU. Let's assume we have an instruction pipeline that is in fact too wide. So we can execute 2 threads in parallel at any given moment. And we have 3 logical threads. So this is the physical resource over here, and these are the logical threads. So for this example, 2 and 3 suffice. Of course, these are hundreds and thousands in practice, right? But it's just for the simplicity. So what happens? Thread 0 now, and also I'm ignoring the warps here, which just assume one thread will be multiple arranged in a warp. So thread 1 issues a load, And this load will stall in the next cycle because it takes a cycle to actually load the memory. Of course, it takes much more than one cycle in practice, but let's assume it takes one cycle here, okay? What happens in this GPU is as we know, the next thread is activated and issues the load, the first instruction of the second thread. And of course, that guy goes to stall. And then the third thread is activated, and you can see over here how we utilize the pipeline. The third thread is activated, and then this guy goes to stall. But when this guy stalls, hey, the first thread is already ready, because it only took one cycle, right? This is the whole point of the GPU. Then it can issue the second instruction, and so on. Then we can do this mult, because now this guy stalls, because the mult needs to be pipelined through the whole business, and then it goes to this. So it's basically this fast context switching of what a GPU really does in practice. And of course, if you do this to the infinite, then you will get a very large utilization of this pipeline, because now we have these two instruction units basically beginning from the second instruction fully used, right? But we have it only fully used if we have these three threads. If we only have two threads, we will not be able to utilize this instruction 100%. So now we see kind of the trade-off. We need enough parallel work to do in order to hide the instruction latencies. So all these numbers need to match up, right? The instruction latency, the work to do, the number of threads, and the width of the instruction pipeline. Of course, what is clear in the practical GPU is that the instruction pipeline has a given size, right? So that's what we bought. These latencies, they will also be fixed, because that's how long the memory takes to deliver a value to my core, to my GPU core. The only thing we can really realistically vary is the number of threads, right? And of course, the instruction stream. Okay, but this is what we do in order to get this very fast on today's GPUs. When you tune a GPU program, you actually care about these things. But now let's assume we don't want to interrupt this nice cycle of issuing loads and stores to memory, but in order to do communication, we just want to introduce new operations in this cycle, and we call them puts and gets. So just as the previous talk mentioned, let's assume we want to hook up BXI to our GPU somehow, magically. And we want to make the GPU communicate directly with another GPU from within its instructions, right? I'm not going into too many details here, but let's assume there's an instruction get and an instruction put, right? So, and these are there to access remote memory, right? GPU memory on another GPU in another node. So how could we do this? Well, basically, it could be the same. Of course, now the stall takes longer, because we now may have to go through half the cluster. It's not just one cycle. In this particular case, it's 3 cycles, as we can see here. And you can see that you issue this get, then you issue the second get, then you issue the second get, and now the problem is nothing is done. So we actually, the GPU here actually has to stall. So we are losing a slot in the pipeline that we could utilize with an instruction. We just don't have an instruction to put it in there, right? So this is, now the big question, is this valuable to add get calls or even put calls to this overall model? So this was the research question we asked when we started this work. So do we have enough parallel slack? It's another way to ask the same question. Do we have enough parallel slack in order to hide the latencies across a cluster? Because what we know for a GPU, that's its design, a GPU can hide the latency of the local GPU memory, which is about 300 to 500 nanoseconds, right? So that's no problem. But as soon as we go to the other side of the data center, that may be 1 microsecond to 10 microseconds, right? So do we have enough parallel slack to do this on today's GPUs? Okay, but now let's go a little bit more into theory, that we understand the background of this. So here is a visualization that my student likes to show, but let's actually go right to the equation. So there is a very interesting, very important law, probably one of the most important laws in parallel computing, and it's unfortunately not known by everybody. It's called Little's law. And Little's law really tells me how much concurrency I need. There are various ways to explain it, but let me explain it here in this way. How much concurrency I need in the number of threads in order to hide a certain latency and achieve a certain throughput. And nicely, this law is extremely simple. You just multiply the latency times the throughput, and you will get to the concurrency, okay? That's wonderful. So one way to explain it is, for example, you want to design the size of a train station. You have 100 people walking in every minute. What has the size of the train station? Actually, 100 people will walk in every minute, and they will spend 10 minutes in the train station. How big has the train station to be, right? So it's 1,000, because you need to have all these people in there, you just multiply the two. Okay, wonderful. If we now do this multiplication for given latencies today for the device memory here, about 1 microsecond latency, let's just assume that's an upper bound, a safe upper bound to the time that the memory access needs to be served on a GPU local DRAM access. We have in the last generation about 200 gigabyte per second. We could easily plug in more modern numbers. And we have about 200 kilobyte data in flight, and that's an application-specific number that we can also change. But for this particular example, we will need 12,000 threads. Right? Okay. So this would actually work. So if we assume that we have an application running on the GPU that can use this GPU efficiently with that working set, 200 kilobyte, then we would need 12,000 threads. The nice piece is if we take an interconnect where the latency is much higher, 7 microsecond, but the key insight is at the same time that the latency is much higher, the bandwidth is much lower. Because of course, going through half the cluster, it means that we achieve a much lower bandwidth. So this means that we will actually need many less threads in order to make this happen. So this was probably one of the key insights, the key scientific insights of this work, where we basically found that, well, yes, if we have a program that runs reasonably on a GPU today, if we extend it to issue remote calls, it'll not get worse. It'll most likely not get worse because the bandwidth is lower. Okay, but now let's get a little bit more into practice. So what did we design? Well, in the design, we call this dCUDA, so distributed CUDA, and the idea is to really extend CUDA directly with MPI3 RMA operations. So without stopping a kernel, from within a kernel, so assume this is now a CUDA kernel here, from within a kernel, we can now issue CUDA, or in this sense, MPI, put, and get operations. So we introduced 3 operations. We introduced a dCUDA put notify, a dCUDA get notify, which is not on the slide, and a dCUDA wait notification. The semantics of these 3 calls are very close to MPI3 one-sided. They're basically the same. We could easily rename them and use MPI3 one-sided concepts, but we decided to not do this in this research prototype. And we can now, actually, without stopping the wonderful overlapping of computation and memory access, we can issue these calls right from the GPU. That means we can use the GPU's hardware that automatically enables overlap of computation and communication directly together with remote communication. So what happens, in fact? Well, what happens here is that this will execute this code, and then as soon as this dCUDA put notify executes, the GPU will issue a request to the whatever communication hardware, let's say it's an InfiniBand driver, will issue the request to the InfiniBand driver, going through more craft than I want to mention here. But then it'll actually be descheduled because it cannot progress, and some other GPU thread will automatically be scheduled. So we get this nice overlap of this nice benefit of overlapping computation communication that we already have for free in the GPU context. Okay? So let me explain it a little bit differently. If we have these 2 devices, and now the question, the obvious question to you is, that you may have is now, of course, well, how many MPI ranks, because I mentioned this is now very close to MPI, how many MPI ranks would we have per device, right? And we just say that the number of MPI ranks per device is the same as the number of blocks, which we limit, of CUDA blocks, which we limit to the number of streaming multiprocessors on the device, because otherwise we have issues with progressing MPI messages and we may run into deadlocks. So if you have 24 streaming multiprocessors on your GPU, you can run 24 ranks on this GPU. Let's assume we have 2 here in this case, so we have rank 1 and rank 2 on device 1, and rank 3 and rank 4 on device 2. So what happens, the nice piece is now that each of these blocks is in fact pretty much equivalent to an MPI rank, so which means it doesn't matter how many you have, you still have one programming model. Even within the same GPU, you communicate through the MPI, through the distributed memory interface to your neighboring ranks, right? And so it's one global programming model. You don't need to worry about shared memory and everything else. It's just magically happening. So here you issue your stencil computation, you issue a put and a wait, and this put will start a communication from rank 1 to rank 2. Here, of course, is rank 2. At the same time, does some stencil computation, but it may actually run on the same resources. This is why it's running a little bit later here. And it issues, of course, a put in this direction and a put in this direction, so there's a 1D stencil here. And then it has to, of course, synchronize, is to make sure that the data that rank 1 started actually arrived at rank 2, because then it moves into the next iteration of the computation, right? And the same over here. And then this guy synchronized because it has to make sure that the data coming from rank 2 actually arrived at rank 1 before it can continue to to compute. But now, this is now looking more like a normal MPI program in the sense, right? You have this put and get. This, of course, it's one-sided, not two-sided, because there is an argument for it why two-sided is not a good idea, but I don't think I have enough time to go into details. If you have any questions about this, either read this paper that's referenced here or talk to me in the break. Okay, what we now see is a wonderful side effect that we have no device synchronization in the sense that we never need to stop a CUDA kernel. Right? So we can actually communicate from right within the CUDA kernel. And if you have experience with CUDA programming, you know that stopping a kernel and starting a kernel is actually a significant overhead. So you don't want to do this very often. But the problem is today you have to do it in order to start any communication to a remote node. You must stop your kernel. And afterwards, if you want to use the GPU again, you must start your kernel, of course. Otherwise, there is no kernel. So then this is the first nice side effect, so we don't need to do this. We just do this from within CUDA. And the second nice side effect is that we can now do this latency hiding, or at least that's the thesis that we still have, that we can actually hide the latency of these puts and gets with the normal GPU switching that's going on anyway in order to hide the memory latency, right? And of course, the complexity goes also down because we have only one programming model. We don't care about GPU programming and MPI programming. We just care about MPI programming. We kind of course, there are still details in order to make this happen, but we don't need to worry about what's on the GPU and whatnot because everything is on the GPU, right? So there's no double memory management. And we have the same communication mechanism for both. So we can issue these puts from within a device, but we can also issue it to another device, and we will see no difference between these puts. So they're basically looking the same. And now the question is, how do we all implement this, or how is this implemented in practice? So this works. In fact, you can download and use this if you want. It's in a research quality implementation state, so that means there may be bugs, and we welcome your fixes. But the implementation is not totally straightforward, but also not too complicated. In the sense, we have these three calls, put, get, and wait. These are a device-side CUDA library, essentially. So you link this library to your code, and this library will in fact communicate with a block manager that sits on the host side. But that you don't worry about in the programming model. This is just a runtime environment now that makes the whole magic happen. And if this wants to send something, let's say this device here wants to send something, it issues through a command queue, a command to the block manager. The block manager will then talk to either MPI communication or InfiniBand directly, which is in this case using GPU Direct, to the remote node, which is over here. Right? And then if there's an incoming message through MPI or InfiniBand, this will go to an event handler and will be dispatched to the right block. So there's one block manager to each block, or for each block on the device. So that's basically a one-to-one relation, which means there may actually be quite some block managers on the CPU, but this works quite well today. So how is the communication actually done? So as we all know, the easy way is to just copy the data from device to the host, to the NIC, to the NIC, to the host, to the device, right? So this is what we call host staging. That was the first way to do this, but in the meantime, we have GPU Direct, which is very simple, where you basically map the PCI aperture space of the device into the NIC, and then you can have a direct DMA communication between the two, and the host basically just instructs the device to do this, right? So GPU Direct will grab the data right from the device to the NIC, to the NIC, to the device without going through the host, right? So we assume this would be faster. What we've observed on a test system that fortunately Hussein gave us access to, we observed a significantly lower latency, but unfortunately a lower bandwidth as well, but that may be a setup problem in this test system that we are still investigating. So now if we compare the two backends that we have for dCUDA, the InfiniBand backend using GPU Direct and the MPI backend, we can see that the InfiniBand backend is significantly faster for, well, of course, the same device put is not affected because it's the same device put. It goes through main memory in both cases. But going to a peer device on the same node or going to a remote device on another node is significantly faster with InfiniBand directly than with MPI, which is of course clear because MPI itself is using InfiniBand, so why should it get faster in order to make this happen? I believe we use the latest MVAPage implementation here to make this happen. And here, the numbers down here are just notification without any data transmission involved. Okay, so, but now let's actually look at the thesis that I stated at the very beginning. Do we actually achieve higher performance? Do we achieve this automatic communication overlap that I've been promising you the whole talk without giving you any numbers? You should be very suspicious at this point. So if you look at a very simple kernel that issues, that's like a stencil computation, but in the stencil computation, we vary the number of iterations per exchange. So we just increase the compute time linearly. So going here from 0 to 30 to 60 to 90, and then of course the execution time increases, which is kind of clear. But we have a constant halo exchange time, so a constant communication time, right? So each of these programs is very simple. It does compute and then halo exchange. It doesn't do anything for overlapping computation or communication. But remember, we have 1,000 threads doing this, and the GPU will automatically switch between these threads. So each of the threads will block. It's programmed in a synchronous blocking manner, but the GPU will automatically turn it into an automatic overlap business here. So if we run it with no overlap, we would get the sum of the two, which is kind of clear, the sum of communication plus computation, which is this line here. But in the actual GPU implementation that we have, we will get somewhat the max of the two, which is very nice. And there is some loss in this very small area here that we can talk about, but that's our runtime system. So now, of course, you may say, well, this all doesn't really matter to me because I don't do micro benchmarks very often. I'm running real code, so we have a set of real codes implemented. Of course, mini applications or proxy applications. Here one is a particle simulation, relatively straightforward particle simulation where we use this current approach that we use in InfiniBand plus CUDA, which is of course using all the latest bells and whistles that we have. So it's using GPU direct enabled MPI implementation, and it's again, I believe, the latest, greatest MVAPage implementation that we are comparing to. And, but of course it has to stop the kernel before it issues a communication, because that's just prescribed by the memory model of today's GPU. And then we have the bound, so this is execution time here, and this is a number of GPUs going from 2 to 10. They're all InfiniBand connected, FDR. And then we have the communication time down here, which is kind of the lower bound, so we can't get faster than just the communication without the computation. And we see that our InfiniBand backend for dCUDA is somewhere in the middle. So it's actually nice because we see this is only gained by automatically overlapping computation and communication, right? So, because this is synchronous programming. We can look at another stencil. This is in fact a stencil that has been extracted from the Cosmo code that we've also heard about this morning. This is weather and climate research code, again, lower bound communication. The current implementation as it's used by Meteo Swiss today, and the dCUDA implementation with the automatic overlap of computation and communication using the InfiniBand backend. Then we have more data, which may get boring at this point, but if we do it for a sparse matrix vector multiplication, we actually see that the gain is not that high, and it's basically comparable, because in the sparse matrix vector multiplication, there is this very nice all reduce when you have this dot product at the end, that you cannot overlap computation and communication for, because the dependency structure is such that you can't, which means basically here, well, our implementation doesn't make it worse, right? It doesn't make it better because it can't automatically overlap it, but it also doesn't make it worse. Then we have power iterations as well, which is also somewhat comparable. It gets better with a very large, okay, 9 GPUs. You may wonder why we didn't test much larger systems. The problem is right now we still need a kernel patch in order to make this happen that allows us to install the right memory mappings, which means we can basically exclusively use Hussein's test cluster and nothing else, because nobody will install the kernel patch on a very large machine like Pitstein yet, but we'll see. So with that, I want to come to a conclusion of my talk. What we basically propose here is to get over the legacy of MPI that we have in today's programming, where we do not integrate MPI and CUDA programming or accelerator programming directly, but we somehow keep them separate. And keeping the separate is rather expensive in the sense that we always need to synchronize these devices going back and forth. Our proposal is to integrate them as tightly as possible, so we really have a unified programming model for these clusters, for these large-scale GPU machines. We propose to not use MPI two-sided for this, for various reasons that I couldn't go into details, but basically Maxime has also mentioned this. MPI one-sided is the great new thing, which enables you wonderful automatic communication, computation overlap if you program it right, and it's faster anyway. So two-sided just has matching overheads, unless you have a BXI implementation in Portals, but still you will pay for the matching, right? So no matter what, where you pay it, you will pay somewhere. And this gives us a nice automatic support for a distributed, somehow a distributed shared memory, or PGAS. It's basically PGAS for GPUs, right? So you can automatically access remote, not automatically, but you can access remote memory through puts and gets. And the nice piece of this, or the scientifically interesting piece, in my opinion, is really that this latency hiding that the GPU is doing today, right? Just to deal with the memory latencies, it's easily extensible to the whole cluster. We have shown that you can overlap these 7 microseconds as well. Actually, talking to NVIDIA, I mean, they're doing this NVLink, which is very, very similar to what we are proposing. They're just lowering the latencies a little bit further, but the idea is very much the same. The problem is NVLink, as it is defined right now, is still an intra-node system, so you can't connect 5,000 nodes with at least the first version of NVLink. And so with this we can hook the whole thing up to InfiniBand and can basically build clusters as large as we can build them reasonably with InfiniBand. So exascale maybe. Okay, so this is what I basically mentioned, and we get this wonderful overlap that I just mentioned. So we have synthetic benchmarks that show perfect overlap, as well as real applications, real proxy applications that show reasonable overlap. And you can download it and play with it and get us feedback. And of course, this was all funded by various Swiss funding institutions, basically the Platform for Advanced Scientific Computing in Switzerland. With that, I'm open for questions. Thank you very much. Yes. So the question is how this will change with GPU direct asynchronous, or the asynchronous version. So this will actually, this is a very good question. So the new features in GPU direct async will actually allow us to improve this implementation, right? However, they will also allow to improve MPI implementation. So they may move closer together, right? So the question is exactly how. The benefit of the better programming model, unified programming model, will still remain, but it shall be seen what actually happens to the performance difference. Yes, it may shrink. Great. And we'll be happy to compare immediately. So NVLink has a different programming model, right? So NVLink relies on the CUDA you run on top of NVLink relies on the C++ memory model, which is different from what we do, because we can argue about this, but I believe the C++ memory model is not the most scalable memory model on the planet, because it always requires to issue, I mean, unless the region-based proposal of NVIDIA makes it into the C++ specification, but at least today, you may have trouble synchronizing large sets of nodes just in the programming model. While this is based on the MPI RMA programming model, which is, in theory, scalable to very, very large numbers, so to millions of endpoints. So the comparison will be hard. Of course, in NVLink, the parameters are much lower than if we go over InfiniBand. That's kind of clear. But we could try it. IB over power.
So instead of using x86 here, use power architect, but still IB. Let's say it's just difficult to compare, but that would be just.
So you mean the InfiniBand hooked up to CAPI directly? That would get NVLink to the, I see. So not CAPI. That would be very interesting, yes. So that would lower the latencies significantly. Thank you very much.